Hello everyone, this is example 3 on flow meters. A venturimeter having a throat diameter of 100 mm is installed in a horizontal 300 mm diameter pipeline carrying a light oil of specific gravity 0.82. A mercury tube connected at the inlet and throat shows a difference in height of mercury columns of 225 mm. The remainder of the tube being filled with oil. So which of the following gives the theoretical velocity at the throat? The volume flow rate Q if the meter coefficient is 0.975 and the meter coefficient if the head loss is 300 mm of oil. So I'll use the equations that I derived in my lecture video on flow meters. So you have to watch first that video so that you can understand the solution here. So this is the situation. Of course, the bigger diameter will have greater pressure, so it pushes this mercury here column. So this should be the configuration, and this is 225. I'll call it Z. The distance from this level to the throat is denoted by Y. So the inlet has a diameter of 300 mm and the throat has a diameter of 100 mm. And the flowing liquid is oil, so this is also filled with oil. So there, I derive a formula for the theoretical velocity at the inlet, and it was equal to area 2 square root of 2gh over area 1 quantity area 1 square minus area 2 square. So theoretical velocity at the inlet is area 2 square root of 2gh over area 1 square minus area 2 square. So therefore, if it is theoretical velocity at the throat, then we just replace area 1, area 2 by area 1. And since area 1 is pi over 4 diameter 1 square, and we have pi over 4 here in these factors here, quantity squared, then exact the square root, so pi over 4, so pi over 4 will be cancelled. So the direct formula for the theoretical velocity at the throat is diameter 1 square root of 2gh over diameter 1 to the fourth minus diameter 2 to the fourth. Remember, we have pi over 4 diameter 1 square quantity square, so it is diameter 1 to the fourth minus diameter 2 to the fourth. Now, what is h? H is pressure head plus elevation head at 1 minus pressure head minus quantity pressure head plus elevation head at 2. So as I said, you have to watch first my lecture video on flow meters so that you know the definition of that small h there. Because the venturimeter is installed horizontally, then Z1 and Z2 will just be 0. So H reduces to pressure head at 1 or in terms of oil minus pressure head at 2 in terms of oil. Now how do we compute this pressure difference or pressure head difference? We sum up pressure, transmission of pressure from fluid mechanics between 0.1 up to 0.2. So we go down along this differential manometer until we reach 0.2. So beginning with 0.1, so the pressure there is P1. So SUP means sum up pressure from 0.1 to 0.2. So P1, we go down, so that's plus. This is oil, so plus quantity Y plus Z. So we reach here, gamma of oil times Y plus Z. We jump across to this point because these 2 points are on the same level, so therefore they have the same pressure and the equation will not change. We are now here. Then go up. This is mercury, so minus specific weight of mercury times Z. Go up again. This is oil minus gamma of oil times Y. Then we reach 0.2, so equals pressure at 2. So simplifying, notice that gamma of oil while Y will be cancelled out. So transpose this to the right. So P1 minus P2 equals gamma of mercury Z minus gamma of oil Z. So that would be the situation. Factoring out Z and dividing everything by gamma of oil, then we have pressure head at 1 in terms of oil minus pressure head at 2 in terms of oil equals Z times quantity gamma of mercury over gamma of oil minus 1. Since gamma of mercury is 13.6 specific gravity times gamma of water, and gamma of oil is specific gravity of oil times gamma of water, we can cancel specific weight of water. So the equation H reduces to Z times quantity specific gravity of mercury divided by specific, so Z quantity specific gravity of mercury over specific gravity of oil minus 1. So solving now for H is 0.225 times quantity 13.6 over 0.82 minus 1. So the value of H is 3.507 meters of oil. Finally, substitute into this equation here. The theoretical velocity at the throat is 0.3 square root of 19.62 times 3.507 over 0.3 to the fourth minus 0.1 to the fourth. So solving for the theoretical velocity, it is 8.347 meters per second. The volume flow rate, if the discharge coefficient of meter coefficient is 0.975, so it is just Q, actual discharge, equals area 2 times meter coefficient C times theoretical discharge, and theoretical discharge is area 2 times theoretical velocity. So Q equals C Q theoretical, and Q theoretical is area 2 pi 0.05 square, because 100 mm is 50 mm or 0.05 meter in radius square, then theoretical velocity at the throat times 1000 to convert it to liters. So Q is 63.92 liters per second. And finally, for the meter coefficient, given the head loss, so if there is head loss and we consider it, then we can compute the meter coefficient. And the formula, which I also derived in my lecture video on flow meters, is square root of quantity small h minus head loss over small h. So this is the formula which I derived. So C is square root of 3.507 minus 0.3 over 3.507. So the meter coefficient is equal to 0.9563. So you can follow this if you watch first my lecture video on flow meters. But you can solve this without using these formulas by first writing energy equation between 1 and 2, neglecting head loss so that you can compute theoretical velocities. Then you sum up pressure from one point to another, just like what we did here, to define that H there. Then you can derive all these things. So that's it.